All right, so today we're going to talk about inverse functions. Inverse functions. And basically what it means when a function is an inverse is that if you compose the inverse and its original function, you're going to get the function x. So suppose that we have a function f of x, and we have its inverse, which is f negative 1 of x. This is how we denote an inverse. If this was g of x, this would become g negative 1 of x, but it means the same thing. It's just the inverse of the original function. So in order for f negative 1 to be an inverse of f, this property needs to hold. It needs to be a function such that f of f inverse of x will give me x, and f inverse of f will give me x. If you're not sure about what this notation means, this is called function composition. So basically the composition of f and f inverse must give me x. If you're unsure how to compose functions, I made a video on that a few days ago. You can go ahead and check that out, but I'm assuming that you know how to compose functions for the purposes of this video. So let's go ahead and do an example problem. So problem 1. Suppose that we have a function f of x equals 1/2 x squared, and I want you to find f inverse of x. Now the way we do this is we first isolate this x. So we solve for x in terms of f of x. Then all we do is switch f of x and x. So let's go ahead and do that. So here we're going to have f of x equals 1/2 x squared. Now we want to isolate the x. So the first thing I'm going to do is try to get rid of this 1/2 by multiplying both sides by 2. So I'm going to have 2 times f of x is equal to x squared. If I multiplied this side by 2, these 2's would cancel, so I just have this x squared left. Now, I want to get rid of this squared. So the opposite of squaring a number is square rooting it. So I'm going to take the square root of both sides, and that's going to isolate the x for me. So I'm going to have the square root of 2f of x equals x. Now the final step is we just want to switch the f of x and x. So we're going to have the square root of 2x is going to equal, instead of f of x, we're going to put f inverse because that's what this function is. So from this, we found that if f of x equals 1/2 x squared, then f inverse of x is the square root of 2x. And now what we're going to do is go ahead and verify this property right here. So we're going to compose these two functions both ways and see what function output we're going to get. If these are indeed inverses and we did our work correctly, we should get the function x in both cases. So let's go ahead and do that. So we know that f of x equals this and f inverse equals this. So let's go ahead and find f of f inverse of x. So the first thing we're going to do is identify what our function f of x is, which is 1/2 x squared. So now instead of x, we're just going to plug in f inverse of x. So we're going to have 1/2 of the square root of 2x squared. Simplifying this, we get 1/2 of the square root of something squared is just going to be that something, so we have 2x. And then these 2's will cancel out, so we have just x. So the first part of this property is verified. Now the second part, f inverse of f, should also come out to x. So let's go ahead and compose those functions. So f inverse of f of x. So our function f inverse is the square root of 2x, but instead of x, we're going to write f of x inside there. So we're going to have the square root of 2 times f of x, which will be the square root of 2 times f of x is 1/2 x squared. So we're going to write 1/2 x squared. Now we just simplify. If we cancel out these 2's here, we have the square root of x squared. And these radicals and squares will cancel out, so we have x. So this indeed is the inverse of f of x. Let's do another example. Let's say we have the function f of x equals 2 over 1 plus x, and we want to find f inverse of x. So let's go ahead and solve this. So the first thing we're going to do is just write out our function. So we have f of x equals 2 over 1 plus x. And now we want to isolate this x. So we want to get this x in terms of f of x. So the first thing I'm going to do here is I'm going to multiply both sides by 1/2, because if I do that, I can get rid of this numerator 2. So if I multiply both sides by 1/2, I have 1/2 f of x is equal to 1 over 1 plus x. Now, I'm going to multiply both sides by 1 plus x. That even though I'm not isolating the x, I can divide out this term once I do that, and then that will allow me to isolate the x. So multiplying both sides by 1 plus x, I get 1 plus x quantity times 1/2 f of x is equal to 1. Now, I can divide both sides by this 1/2 f of x. So I have 1 plus x equals 1 over 1/2 f of x, which is the same thing as saying 2 over f of x. Now I can subtract 1 from both sides, and I get x equals 2 over f of x minus 1. Now the final step, all I need to do is switch out this f inverse with this x and change the, this f with x, and then change the f of x to f inverse. So my final answer is going to be f inverse of x is equal to 2 over x minus 1. Let's go ahead and verify that these are inverses by composing the functions once again. So just a reminder, our original function was 2 over 1 plus x, and our inverse function is 2 over x minus 1. Now we're composing f and f inverse. So all we're going to do is plug in f inverse wherever there's an x in f of x. So we're going to have 2 over 1 plus, there's an x there, so we're going to plug in f inverse. So we're going to have 2 over x minus 1. Simplifying this, we have 2 over this 1 and the negative 1 will cancel out. So we have 2 over x. And then this is the same thing as saying 2 over 1 times the reciprocal of the denominator, so x over 2. And these two again will cancel out, so we're just having x. Now let's verify the other composition, f inverse of f of x. So we're going to take f inverse, and wherever there's an x in f inverse, we're going to plug in the original function f of x. So we're going to have 2 over, there's an x in our inverse function, so we're just going to plug in f of x there. So we have 2 over 1 plus x, and then we have a minus 1. So now simplifying this fraction right here is going to be equal to 2 over 1 times the reciprocal of the denominator, so 1 plus x over 2, and then we still have this minus 1 at the end. These 2's will cancel out again, so we have 1 plus x minus 1, and 1 minus 1 is 0, so we're just going to have x. So that's how to find inverse functions and verify them algebraically. But there's another interesting property about inverse functions. If I graph an inverse function and the original function, so let's take our previous example. So I have the function f of x equals 2 over 1 plus x. So if I go ahead and graph that, f of x equals 2 over 1 plus x. This is what my function is going to look like. And then I'm going to have its inverse, which we saw was 2 over x minus 1. Now if you notice, this seems to be like a reflection. If I draw the line y equals x, you can see that it's neatly symmetrical on either side of this line. The same thing holds true for our previous examples. So our previous example, f of x was 1/2 x squared. And if we graph its inverse, which was the square root of 2x, we can see that again, it's neatly symmetrical along this line y equals x. So the other interesting property about inverse functions is that once you graph them, f inverse of x will be a reflection of f of x over the line y equals x. So there's three main properties of inverse functions that you should know. One, f and f inverse composed will give me x. Two, f inverse composed with f will give me x. And three, this property, f inverse will be a reflection of f of x over the line y equals x. So that's how to find inverse functions algebraically, verify that they're inverse functions algebraically, and verify that they're inverse functions graphically. And we're done.